All right, hello fellow sapiens. Sit back, relax, and prepare to return to the last day on Earth, 66 million years ago, the day the dinosaurs watched their world end. A quiet moment before history changed forever. This is Sleepless Homo, soft science, slow storytelling, and deep time for the tired minds who wander here at night. A place where we study the past gently, like researchers brushing dust from a fossil, unsure what memory will surface next. Now imagine this, a world waking up for the last time but with no reason at all to suspect it. A calm dawn drifting across a planet that believes it still has millions of quiet mornings ahead. The light spread slowly across the Cretaceous, soft and gold, touching forests that have never heard the word ending. And somewhere inside that light, inside the breath of a warm, ancient wind, lies the question we can never quite answer. How do you describe a world that doesn't know it is living its final sunrise? The Earth of this distant morning is not the one you and I know. It is warmer, thicker, almost heavy with life. The continents stand in different places, drifting on tectonic plates that move too slowly for any creature to notice. North America is split by a wide, shallow inland sea. South America and Africa sit far apart, their once shared edges now strangers separated by deep water. To the north, a proto-Australia clings close to Antarctica, both wrapped in climates more temperate than their modern descendants. Asia stretches broad and ancient, its mountain chains rising but not yet resembling the forms we walk today. The air itself feels different. Oxygen rests slightly higher than in our time, feeding giant ferns and conifers that reach upward with a confidence only ancient plants possess. Carbon dioxide hangs thick but stable, warming the globe into a greenhouse world. When the sun rises, it meets an atmosphere that scatters light through faint haze and high clouds, shaping a daylight softer than the sharp blue many of us grew up beneath. To breathe here would feel strangely full, almost sweet. And yet, for all its warmth, this is a planet in perfect equilibrium. Nothing hints that equilibrium can shatter in a single moment. The forests of western North America greet the morning first, towering angiosperms, still relatively new in Earth's history, unfurl their leaves to catch the light. Beneath them grow understories thick with cycads, ferns, and flowering shrubs that perfume the air with chemical signals meant for pollinators. Each scent is a tiny conversation between species, a coded language built over countless generations. You can almost imagine the forest humming with these signals, a living net of communication held in leaves and petals. Insects stir first. Dragonflies glide low over wetlands fed by warm groundwater. Early bees trace slow circles above primitive flowers. Their wings glitter in the first beams of sunlight. On tree trunks, beetles crawl out from the shadows, their iridescent shells reflecting specks of gold. Ant colonies, patient and disciplined, begin the day's search for food, moving in narrow, purposeful lines. These creatures do not imagine tomorrow. They follow the same rhythms their ancestors followed for millions of years. Along the rivers of the coastal plains, hadrosaurs wander in peaceful groups, their crests resonating with low, conversational calls. Their footsteps leave deep impressions in the soft sediment. Some pause to drink from the water's edge, where small fish scatter under the disturbance. Above them, pterosaurs trace lazy arcs across the sky, their wings catching the warm morning thermals that rise from the land. They have flown here for ages, long before birds refined the art of flight into something narrow and delicate. On this morning they glide as they always have, unaware that their silhouettes will soon vanish from the world forever. Farther inland, forests shift into drier woodlands and open fields. Triceratops graze in slow, rhythmic patterns. Each movement is deliberate and unhurried. Their horns cast long shadows against the grass as the sun climbs a little higher. In the distance, a single Tyrannosaurus rex stands still among the ferns, listening. Its senses are exceptional, vision sharp enough to track movement over great distances, hearing tuned to low vibrations, olfactory nerves capable of pulling scent from the wind. Yet even a predator with such awareness cannot detect the truth written silently across the sky. It merely inhales the morning with the same instinctive expectation that today will resemble yesterday. The climate on this final morning is steady. Sea levels sit high across the globe, swallowing coastlines and flooding continental interiors. Warm oceans fuel predictable storms. Tropical regions stretch far from the equator, creating vast belts of humidity that nourish dense vegetation. Temperate zones, too, lean warmer than ours. Even near the poles, forests stand green and thick, home to hardy species that survive months of twilight rather than months of frozen darkness. This is a planet shaped by warmth and abundance. A soft wind pushes across the plains. It carries pollen from flowering trees, dust from distant deserts, and the faint mineral scent of volcanoes that rumble quietly along ocean ridges. Earth's crust never sleeps, but today its movements are calm, nothing more than the subtle restlessness of a living world. Rivers run in slow curves, reshaping sediment deposited by countless storms. Lakes shine under the sun like enormous mirrors. Reptiles bask on flat rocks, letting the light seep into their cold-blooded bodies. Everything here exists in a gentle balance. As the sun rises higher, the sensory world unfurls. Forests echo with the deep vibrations of hadrosaur calls and the sharp clicking of small predators moving through underbrush. The air is full of insect murmurs. Tree canopies shake with the movements of early birds, their feathers catching new light. In shallow seas, marine reptiles glide through currents warmed by greenhouse oceans. Coral reefs flourish in colours no eye from our time has ever seen. Even the beaches glimmer with life, their sands trembling under the tiny movements of crustaceans buried beneath the surface. It is strange to imagine so much motion existing in such quiet harmony. If you stand here long enough breathing this air, listening to this world, you might feel a strange ache. Perhaps it comes from knowing something that no living creature of this time could know. You and I carry the weight of hindsight. They do not. They wake, feed, groom, move, fight, rest, and expect the same tomorrow. None of them sense that their planet is already carrying a secret. Not a warning, not a threat. Just a fact drifting toward them with perfect indifference and perfect precision. Still, the morning continues, the air warms, shadows shrink, a symphony of life fills the landscape, playing the same ancient melodies it has practiced across millions of years. To look across this world is to witness a story that does not yet realize it is reaching its closing lines. For now, everything is familiar, everything is stable, everything is alive. Somewhere in a dense coastal forest, a group of small feathered dinosaurs picks insects from tree bark. Their bright eyes blink at the sun's glare. They hop along branches with a confidence that comes from having survived countless seasons. Their feathers catch the wind, dusting the air with loose fragments. They do not sense any change in the forest's rhythm. The trees sway with the same old motions. The insects buzz with the same casual urgency. The world seems permanent. Out on the open plains, larger herbivores cluster near watering holes. The heat of the day draws moisture into the air. Thin clouds form far away, promising a light afternoon rain that will keep the grasslands green. Along the horizon, Distant mountain chains glow faintly in the sun, ancient and unmoving. Nothing here carries the signature of finality. Nature does not hint. It simply moves. Imagine sitting here beside a quiet pool of water, listening to the soft trickle of the stream feeding it. The surface reflects the canopy above, broken only by the ripples of small creatures moving beneath. You watch the sunlight dance along the water's edge. You feel the warmth rising from the ground, and for a moment you might almost forget what this world is about to face. That is the strange burden of knowledge. To witness beauty knowing it stands on the edge of disappearance. Scientists today try to reconstruct mornings like this using fragments, preserved pollen, isotopic signatures, sediment layers, fossilized plants, and the delicate impressions of leaves once pressed into mud. It is not perfect. It never will be. But each piece helps us imagine a world that vanished long before our ancestors dreamed of walking upright. We cannot claim certainty. We only know what the rocks whisper when we listen carefully. By midday, this final morning has settled into calm routine. Forests breathe. Plains shimmer with heat. Creatures go about their lives unaware that their world has already entered its last chapter. Nothing in the sky looks different. Nothing in the ground vibrates with warning. Nothing in the air carries the metallic scent of change. In this moment, Earth stands exactly as it has for ages, abundant, warm, and utterly unprepared for what will soon arrive. This is the world we're trying to understand, a world whose last morning looked as ordinary as any other. A world that teaches us a quiet truth. Endings often arrive disguised as normal days, carrying no announcement except the stillness that comes before a storm. And somewhere above all this life, beyond the reach of any creature's senses, something begins to shift. But that belongs to another page of the story. For now, we sit with this morning, the last normal morning Earth would ever see. If you're new, feel free to subscribe, not for numbers, but so more sleepless thinkers can find calm education in a loud world. And if you've been here before, welcome back. I'm glad you're still wandering through time with me. Tell me, where do you listen? While trying to fall asleep? On long drives? At work? Cooking? Walking? Or somewhere between all of them? I always read your answers, and if you drift off, don't worry. There are timestamps waiting for you when you return. All right, let's continue. And as always, stay curious. Stay calm. Imagine this. High above the calm forests and warm seas of the late Cretaceous, far beyond the clouds and the reach of any wing, a silent shape drifts through space. No creature on Earth can see it. No eye has evolved to look that high with purpose. Yet there it is, hours away from the moment that will change everything, crossing into the invisible territory where Earth's gravity begins to pull with more insistence. This is the part of the story where nothing on the ground stirs, but the sky itself has already begun to shift. To understand this arrival, we must begin even farther away, in a region no living being from that world could ever imagine. Somewhere in the outer reaches of the solar system lies the asteroid belt, a vast and ancient cemetery of fractured planets and failed beginnings. Among these scattered stones, collisions have been happening since the solar system itself was a swirling disk of dust and light. Each impact reshaped the fragments, sending some spiraling inward, others outward, and many simply spinning in their eternal orbits. According to the best evidence we have, the chicxulub impactor likely began its long journey here, shaken loose by gravitational disturbances millions of years before this final morning. Scientists believe it may have been part of a larger asteroid family that broke apart after a violent collision in deep time, a collision so old that Earth still belonged to reptiles the size of small dogs, and flowering plants had not yet appeared. From that ancient event, one fragment began drifting along a new orbit, nudged again and again by slight gravitational interactions with Jupiter, the giant of our system. Jupiter, with its immense mass, reshapes the fates of stones without effort. A slight tug here, a subtle deflection there, and an asteroid that once circled peacefully in the belt finds itself falling inward, its path gradually bending toward the sun. Nothing about this process is intentional. It is simply physics unfolding over unimaginable stretches of time. But eventually, that falling path brought the chicxulub body close enough to Earth's orbit for both worlds to intersect. What happens next is not a collision in the dramatic sense. It is more like two lines drawn across the same map finally crossing, though one line happens to be a planet and the other happens to be an object weighing billions of tons. As the asteroid enters the region astronomers call Earth's gravitational sphere of influence, its journey transforms. It is no longer drifting freely. It is falling. This subtle shift begins hours before impact. If you could watch from high orbit, you would see Earth's pull accelerate the rock, drawing it faster and faster toward the blue-green world below. Its velocity, already immense, begins to rise. The numbers we calculate today are staggering, but here we speak in calm terms. It approaches at many tens of thousands of kilometers per hour, a speed no creature of that era had any concept of. The asteroid itself is not glowing yet. That is an important detail. In popular imagination we often picture incoming fire, but real fire begins only when something enters the atmosphere. Out here, above the thin veil of gases that protect the planet, the object is cold, indifferent, and unimaginably quiet. Sunlight washes over its fractured surface, revealing patches of metal-rich stone formed in the earliest days of the solar system. If you could touch it, you would feel a roughness shaped not by weather, but by eons of cosmic radiation and the distant debris of other worlds. As it falls closer, subtle interactions begin. Earth's gravity stretches the asteroid slightly, not enough to break it, but enough to stress the minerals deep within. Tiny microfractures shift. Grains of dust trapped in cracks vibrate. The object does not feel any of this, of course. It is simply obeying the geometry of gravity. But this is where its long sleep ends. For millions of years it drifted without consequence. Now every second increases its speed. By the time it reaches the altitude where low-orbit satellites circle today, it moves with a momentum that no natural force on Earth's surface could replicate. Meanwhile, far below, the planet is calm. Clouds move in their usual patterns, winds cross the continents, the sun warms oceans filled with ancient creatures, forests breathe in slow pulses. Nothing hints at what approaches. But if one could rise high enough, into the thin blue curve where the atmosphere ends, one would notice something extraordinary. The asteroid is being bent. Its trajectory is no longer a straight line. As it enters thicker layers of Earth's gravitational influence, the planet begins to steer it, curving its path toward what will become the Yucatan Peninsula. It is not a matter of destiny, only of geometry. Earth rotates. The asteroid falls. Their motions intersect in one precise place. There is a strange beauty in such inevitability. Not a story of intention or fate, but of physics meeting biology at a single point in time. It reminds us that planetary history is shaped not by meaning, but by conditions, by chance alignments of mass and motion that create outcomes far bigger than the forces that caused them. As the hours dwindle, the asteroid draws even closer. If you floated beside it, you would see Earth growing vast beneath you. Swirling clouds, continent outlines, shimmering seas reflecting sunlight. At this distance, the atmosphere becomes visible as a thin, delicate layer hugging the planet. A fragile membrane only a few dozen kilometers thick. It is this membrane that will determine everything that happens next. But for now, the asteroid has not touched it. It is still falling through vacuum, silent and cold, carrying the accumulated momentum of its entire cosmic journey. The object is roughly 10 kilometers across, though some estimates vary. To imagine its size, picture a mountain drifting through the sky, moving so fast that it completes the distance between horizon and horizon in less than the time it takes to breathe. And yet it offers no spectacle at this distance. There is no roaring sound, no glow, no drama. It appears almost peaceful, a solitary stone descending through the emptiness between worlds. Earth's gravity continues to accelerate it, feeding energy into its fall. Its speed increases by thousands of kilometers per hour in the last moments. These are numbers we struggle to comprehend in daily life. But nothing about this story belongs to daily life. This is a planetary scale event, and the physics that shape it follow rules most of us encounter only in textbooks or theoretical models. Scientists today use computer simulations to reconstruct these final hours. We feed in data about asteroid density, composition, velocity, and angle of entry. We include estimates of Earth's atmospheric structure as it existed in the late Cretaceous. Each simulation gives us slightly different variations, but the broad picture remains consistent. The asteroid approaches at a steep angle, between 30 and 60 degrees above the horizon. That angle matters. Too shallow, and it might have skimmed the atmosphere. Too steep, and the impact dynamics would have changed dramatically. But this angle lands in the middle range. Efficient, focused, catastrophic. Still, at this point in the story, nothing has happened on Earth. The forests remain undisturbed. The oceans continue their slow rhythms. The creatures going about their morning routines have no reason at all to lift their heads. The asteroid is far above their awareness. The air does not tremble. The sky does not darken. Even birds flying at their highest altitudes would not notice anything unusual. This is what makes the moment so haunting. A world utterly unaware, and an object utterly committed to its path. As the rock draws near the upper boundary of the atmosphere, subtle heating begins. Not fire, not yet, but a whisper of thermal energy building along its forward edge. The air is still too thin to ignite anything, but the molecules it encounters begin to compress. The leading surface warms. Dust particles trapped in its cracks begin to glow faintly. If one were watching from space, the asteroid would appear as a dim spark against the dark. Not enough to alarm any hypothetical observer, just enough to announce that it has nearly arrived. This is the last true moment of peace. Not peace on the ground, because nothing is happening there, but peace in the sky, the absence of the violent transformations that will begin the moment this rock touches the atmosphere. In another breath, it will cross into air, and air is not empty. It is matter, and matter resists intrusion at these speeds. From here, everything will change very quickly. The asteroid will ignite, the atmosphere will roar, the ground will soon feel consequences that no living creature has ever experienced. But those belong to another step in the story. For now, the object remains suspended in the thin, glowing boundary, where space begins to remember that a planet lies below. This is the moment the Earth becomes aware of the visitor it never invited. And this is where we pause, not because the story slows, but because the world below is still innocent of what fate is rushing toward it. A single point in the sky becoming brighter than the sun itself. Not over minutes or even seconds, but instantaneously, so fast that no creature on Earth could blink in time to protect its eyes. A light so intense it erases every shadow, every colour, every distinction between forest and plain. For one impossible moment, the world becomes a sheet of white, as if someone has peeled back the surface of reality and exposed the raw energy beneath it. What kind of light can do that? And what does a planet experience in the final second before it is struck? To understand this moment, we have to step into the thin blue layer where air begins to matter, just a breath above the highest pterosaur flights, just beneath the boundary where space lets go. The asteroid finally meets the atmosphere at full speed. The numbers are difficult to imagine in human terms, but what matters is this. The asteroid hits the air with so much force that the air cannot move out of the way. Instead, it becomes something else altogether. It becomes compressed to the density of solid metal, heated to temperatures far beyond any natural fire, and then forced outward in a shock that travels faster than sound can carry meaning. This is where light begins. As the rock slams into the upper atmosphere, molecules of nitrogen and oxygen are crushed into states rarely found outside nuclear detonations. The friction is not friction in the way we understand it. It is not rubbing. It is violent compression, billions of air molecules smashed in front of a mountain-sized object, travelling faster than the mind can comfortably hold. This compression instantly converts kinetic energy into heat, and that heat becomes light. Not gentle light, not the warm glow of sunrise. This is thermal radiation so intense that the atmosphere itself shines. The asteroid begins to vaporize before it even descends a single kilometre, but the vaporization is not the source of the flash. The flash comes from the air being forced into plasma, a state where electrons tear free from atoms, and the atmosphere behaves more like a star than a gas. In that flash, the air becomes a brief artificial sun. On the ground, the effect is immediate. Across much of the continent that would later be called North America, everything facing the direction of the impact point is washed in a sudden white brilliance. Shadows disappear. Night becomes day for regions still in darkness. Dawn becomes something unrecognizable, a raw brightness not filtered through clouds or atmosphere. Even creatures miles from the coast, deep in forests or across open plains, witness this unnatural illumination. Their eyes, adapted to a world of steady sunlight, cannot interpret it. Some freeze. Some flee without direction. Some simply stand still, unaware that the world has already changed in ways they cannot understand. In the last second before impact, the physics intensify beyond ordinary comprehension. As the asteroid plunges through thicker air, the compression wave grows stronger. Pressure skyrockets. Temperatures spike to levels that rival the surface of stars. The air becomes an incandescent shield in front of the descending object, glowing so brightly that the asteroid itself is hidden behind it. If you could remove the atmosphere for a moment, the rock would still appear dark and cold. But through the atmosphere, it becomes a streak of pure radiance. That radiance expands. A halo of thermal energy spreads outward from the point of entry, washing across the sky in expanding rings of light. These rings are not visible in the way sound waves are heard. They are flashes of ionization, invisible to us, but overwhelming to any photoreceptor designed for life on Earth. Birds in flight are momentarily blinded. Creatures on the ground squint instinctively or turn away. Even animals without complex vision feel the change as the heat wave penetrates their skin. The flash carries not only light but searing infrared radiation, the kind of heat one might feel standing too close to a forge, amplified across hundreds of kilometers. As the asteroid descends, the final fraction of a second stretches into an eternity of physical transformation. The pressure at the leading edge grows so intense that the rock itself begins to flatten, like a stone striking water, though it barely has time to deform before being destroyed. The air in front of it is compressed into a shock wave that pushes downward toward the surface, travelling at a speed faster than the object itself. This shock wave hits the shallow sea off the coast of the Yucatan Peninsula 100,000th of a second before the asteroid does. The water responds instantly, but that part of the story belongs to another page. For now, we focus on the light. What follows next is the moment when the brightness peaks. If you stood anywhere within 1,000 kilometers, you would see a flash so intense that it overwhelms the sun by orders of magnitude. It is not a beam, but a hemisphere of radiance expanding outward. For a brief instant, the Earth becomes illuminated from a point not in the sky, but on its own surface. Trees cast no shadows because all their edges glow. The surface of lakes and rivers turns white. Mountains appear flat, stripped of texture. The world looks as though someone has taken the idea of light and accelerated it beyond the threshold of human experience. To describe what animals saw is difficult, because nothing alive today has encountered anything like it. The closest analogy we can use is the flash of a nuclear detonation, but even that fails to capture the scale. The brightness across the continent would have risen gradually over a few milliseconds, a rise so fast that the eye could not process it. Retina cells would have responded all at once. Vision would have filled with white. Some animals might have closed their eyes instinctively, but it would not have mattered. The eyelid is not enough to protect against this kind of radiative power. Even with eyes shut, the world would still have glowed through the thin membrane of skin. What makes this moment especially strange is that it happens before the asteroid reaches the surface. The ground beneath is still intact. The forests still stand. The creatures that will soon feel the force of impact are still alive, still sensing the world as they always have, except for the overwhelming light that has turned their environment into something alien. Light travels faster than sound, and faster than the mechanical shock waves that will follow. In this one instant, the Earth is reacting only to photons, not to force. The energy of the flash outruns every other consequence. The physics underlying this moment are grounded in models developed by impact researchers using supercomputer simulations. They calculate how the atmosphere behaves when compressed by an object of this size and speed. They consider the angle of entry, the velocity of descent, the density of the rock, and the structure of the atmosphere in the late Cretaceous. These simulations tell us that the thermal pulse released in the first millisecond could have ignited dry vegetation instantly if dryness were present. But in the humid coastal regions near the impact site, the vegetation was likely damp, so the initial flash did not create flames on the ground. Instead, it created blindness, heat shock, and a sudden burst of infrared radiation that stunned the senses. Even far from the direct line of entry, the sky brightened. Light scattered through the atmosphere, bouncing among particles and droplets, diffusing across the horizon. Animals facing away from the impact might have seen the world glow behind them. Shadows stretched and flickered in unnatural patterns. For creatures accustomed to the steady rise and fall of sunlight, this sudden change must have been impossible to interpret. There is no evolutionary memory for such an event. No instinct prepares an animal for a second sunrise brighter than the real one. Then comes the first millisecond after impact. In that tiny window of time, the radiant energy spikes again. The instant the asteroid meets the surface, whether land or sea, it releases more energy than the largest volcanic eruptions in Earth's history. The impact vaporizes rock and water, producing an expanding column of plasma that pulses outward with light of its own. This secondary flash is even brighter than the entry flash. Across vast distances, creatures experience another instant of overwhelming brightness, even if the physical shock has not reached them yet. The ground does not tremble at this stage. The air does not roar. But the light says everything. It tells a story of sudden transformation, of physics operating on a scale far beyond anything life is built to withstand. It is tempting to imagine this moment as chaotic, but in truth it is orderly. It follows the laws of conservation of energy, thermodynamics, and radiative transfer. Every photon released has a calculable origin. The brilliant flash is not magic. It is mathematics unfolding faster than the eye can interpret. Yet to the creatures who witnessed it, it would have felt like the world tearing open. A brightness so complete that it erased the boundary between the familiar and the unknown. After this millisecond, the story moves into shock waves, heat fronts, and atmospheric devastation. But those belong to another part of the narrative. For now we linger in the moment of light, the moment when a falling stone turned the atmosphere into a brief star, the moment when shadows vanished and the world was illuminated from within, the moment when the era that had lasted for millions of years ended not with darkness, but with brilliance. And perhaps the most humbling truth is this: even with all our simulations, all our instruments, all our models, we can still only approximate what that light looked like. The rocks preserve its effects, not its appearance. We reconstruct the past with the fragments we have, fully aware that some details may remain beyond our reach. That uncertainty is not a weakness. It is a reminder of how vast Earth's memory is, and how small our window into it can be. The surface of the Earth rising up to meet the sky, not metaphorically, but physically, as if the ground itself were trying to recoil from what has just arrived. The impactor, a 10-kilometre wide fragment of ancient stone, has struck the shallow sea at the edge of the Yucatan with a violence that exceeds anything this planet has experienced in hundreds of millions of years. In the first instant there is no crater, no depression, no familiar shape. There is only vaporized water, vaporized rock, and the beginning of a hole being carved into the crust faster than the brain can form the idea of speed. How does a world respond when struck by an object moving faster than sound in steel? It responds by unmaking a continent. For a moment so short it barely qualifies as time, the asteroid disappears entirely. It does not slow. It does not deflect. It does not glance. It is annihilated. The energy of its fall converts it into a plume of plasma and dust, a column of superheated material rising upward as the shock of impact pushes downward. The rock beneath the shallow sea does not crack at first. It behaves like a fluid, forced aside by pressures so high they turn solid stone into something that flows. This is not melting in the familiar sense. It is deformation under colossal stress, where the minerals that once formed igneous and limestone layers lose their shapes and identities in a single catastrophic moment. The forming crater grows downward faster than mountains rise upward in geological time. In the first second, it is already kilometers deep. The water above it has been vaporized entirely, blasted outward as steam and shattered droplets. Beneath that space, the bedrock bends as if made of wax, pulled toward the center, and then forced sideways by the violence of the impact. Seismic waves begin radiating from the point of contact, travelling outward through the crust, shaking the continental plates with frequencies so intense that the ground behaves like a trapped liquid. These waves will circle the Earth again and again, but in this minute we stay at the centre of the event, where the crust is experiencing pressures it has not felt since the early days of planetary formation. As the shock wave forces the crater to grow, the rock beneath rebounds. This rebound is one of the strangest features of large impacts. When a depression becomes deep enough, the compressed rock below behaves like an over-squeezed spring. It pushes back, upward, creating a central peak that briefly rises higher than any mountain on Earth before collapsing under its own instability. The physics are counterintuitive but well modelled. The ground falls, then rises, then falls again. In that rise, the crust lifts a giant column of fractured stone into the air, only for it to slump outward, collapsing into a ring of peaks around the crater's centre. This is how peak rings form, structures we still see on the Moon and other planets where large craters remain preserved. At Chicxulub, this peak ring will become one of the defining features of the hidden crater, now buried under layers of younger sediment. It is composed of material that once lay kilometres beneath the surface, suddenly hoisted upward and thrown outward in just moments. Drilling into this ring today reveals shocked minerals, fractured layers, and rocks altered by pressures so extreme they form new crystalline structures. Some of these structures cannot be produced by any terrestrial process except a major impact. They stand as signatures of the violence of that minute. As the crater deepens and widens, shock metamorphism begins to leave its imprint. Quartz crystals, stable under the pressures found in mountain ranges or volcanic systems, are shattered into forms known as planar deformation features. These microscopic scars record the exact moment when pressures hundreds of thousands of times greater than atmospheric levels pass through them. Quartz that experiences such force becomes something else. Shocked quartz, a material that reveals the story of the event with no ambiguity. Wherever we find shocked quartz on Earth, we know something extraordinary happened there. And at Chicxulub we find it in abundance. Along with shocked quartz comes suevite, a type of rock formed from molten fragments fused together during the impact. To imagine suevite picture rock being thrown through the air in a half-molten state, then falling back into the forming crater and welding together upon landing, it is messy, chaotic, and unmistakably the product of a violent moment. Drilling cores from the Yucatan show layers of suevite sitting above the deeper impact melt, telling researchers exactly how the crater filled once the initial excavation ended. Under the waterline, the sea floor is being physically removed. Gigatons of sediment, carbonate rock, and ancient reefs are vaporized. The molten cavity that replaces them is enormous. Estimates suggest the growing crater reaches roughly 180 kilometers across before stabilizing. It is difficult to visualize something so large forming in less than a minute. The Grand Canyon took millions of years to carve. This crater formed in the time it takes to warm a cup of water. The edges of the crater are unstable, collapsing inward as the walls slump. This collapse produces additional faults and fractures that radiate outward, reshaping the underwater landscape for hundreds of kilometers. These faults will persist for millions of years, long after the ocean returns and buries the crater under new layers of sediment. Even now, with modern seismic imaging, we can trace the ghost of these fractures deep beneath the limestone of the Yucatan Peninsula. They show us that the continent itself moved and deformed under the load of the impact. Meanwhile, seismic waves travel deeper into the crust, reflecting off boundaries between rock layers. Some of these waves travel at speeds of several kilometers per second, faster than most natural earthquakes. They reverberate within the mantle, bouncing upward and downward. For a moment, the entire region becomes a resonating chamber of force. Rocks that once lay still for tens of millions of years vibrate with intensity, and then those vibrations spread outward, weakening structures far from the point of impact. The central transient cavity, the first version of the crater, begins to collapse under gravity's influence. This collapse is part of the process that creates the final shape. a shallow bowl surrounded by a raised rim, and, within that rim, the peak ring formed by the earlier uplift. Molten rock fills the bottom of the crater, creating a pool of liquid stone that will take years to fully cool. Above that molten pool rise clouds of steam and vaporized minerals, but here we do not follow the clouds. We remain at the ground, where the crust is still trembling from the violence. At this scale, the line between melting and vaporizing blurs. Carbonates, evaporites, and other minerals in the region vaporize and enter the plume. Silicates melt. Limestone breaks down. Some materials are reduced to microscopic droplets. Others remain in molten rivers. All of them, however, are part of the same story. The Earth being sculpted by an event driven purely by physics, not intention. As the minute ends, the worst of the crater-forming phase has passed. The peak ring stabilizes. The wall stops slumping quite so rapidly. The molten lake begins to spread. The crust adjusts to the immense new depression carved into it. Nothing on the ground resembles the quiet, stable world that existed only minutes before. The shallow sea that once covered the coastline is gone. The ocean floor has been replaced with vapor and melt. The land beneath the water has been rearranged entirely, like clay struck by a hammer. And yet this moment is only the beginning of the aftermath. The crater will cool. Sediments will bury it. Life will eventually return, not knowing what lies beneath. But for now, the Earth has been reshaped in less than a minute. A continent has been struck, folded, melted, and undone. The crust has reopened a wound that will remain visible in geological records long after every creature alive that day has vanished. In the deep silence that follows the initial explosion, the crater glows with its own heat, a molten reminder of how fragile continents can be when faced with the violence of cosmic chance. And that silence, too, will not last. An ocean that does not ripple or swell or surge in the way we understand waves, but instead lifts. Not from wind, not from tide, but from the earth itself being struck so violently that the sea is forced upward in a single impossible motion. For a brief moment, water behaves like a solid sheet, rising higher than mountains before gravity remembers its role and pulls it down again. What does a tsunami look like when it is born not from storms or shifting plates, but from the entire planet recoiling from an impact? To picture this moment, we return to the shallow sea that once covered the coastline of the Yucatan. Minutes earlier, this water had been calm, warmed by a greenhouse climate, home to fish, ammonites, marine reptiles, and reefs built by corals far different from the ones we know today. That sea vanished in an instant when the asteroid struck. It did not splash. It evaporated. The first contact between rock and planet converted cubic kilometers of seawater into steam, blasting it upward in a column that rose faster than the mind can grasp. But once the air clears just enough for water to behave like water again, the true consequence of the impact begins. At the center of the forming crater, the ocean floor has been removed. Not scraped away, not shifted aside, but physically blasted into the air as vapor, melt, and shattered rock. In its place is a void, a cavity so deep that the remaining water rushes in to fill it. This inward collapse is the first step in creating one of the most powerful waves the Earth has ever generated. The surrounding sea accelerates toward the crater with unimaginable force. When that water meets the rising walls of the newly formed basin, it rebounds outward, and this rebound is where the mega tsunami begins. Modern tsunami science helps us reconstruct this event, though the numbers strain at the limits of our models. Tsunamis triggered by earthquakes often begin with waves just meters high near their source. Here, the wave height near the impact is measured not in meters but in hundreds of meters, perhaps more. Some models suggest initial waves approaching a kilometre in height radiating outward from the blast zone. These are not waves in the traditional sense. They are walls of displaced ocean, their leading edges carving deep channels into the seafloor as they accelerate. They carry sediment, shattered coral, chunks of carbonate rock, and the remains of any marine creature caught in their path. Near the epicenter, nothing survives this motion. The seafloor buckles as water rushes over it, and the marine ecosystems that once thrived here vanish in seconds. But as the waves travel outward, they evolve. They lose some height, but gain extraordinary reach. Unlike storm waves, which break quickly, tsunamis move as entire columns of water. Their energy is stored not in their surface, but in their depth. And here, the depth is enormous. With the entire ocean displaced, the waves move outward at speeds comparable to jet aircraft. They race across the shallow waters of the Gulf of Mexico, pushing sediment in front of them, tearing up the continental shelf and reshaping the coastal landscape long before any creature on shore can react. One of the most remarkable aspects of this moment is how little the Earth's rotation slows them. The waves, driven by initial displacement, push outward along coastlines, rebound off shallow shelves and rip through underwater canyons. Their paths can be traced today in the deposits left behind. Layers of sand and rock found deep inland in regions of North America show sorting patterns unique to tsunami transport. These sediments provide a quiet, geological witness to an event so vast that no living eye survived to see it. As the first waves leave the Gulf, some travel east toward the ancient Atlantic Ocean. They encounter deeper water and spread out, their heights lowering but their speeds remaining immense. These waves would have crossed entire ocean basins within hours, their energy dissipating slowly but relentlessly. Models suggest that some of them struck coastlines thousands of kilometres away, scouring beaches, ripping forest from shorelines, and depositing marine debris far inland. We know this happened because the rock record holds pieces of coral and deep ocean microfossils in places they should never have reached without an event of extraordinary magnitude. But the most violent waves travel westward. They entered the inland seaway that divided North America into eastern and western continents. This body of water stretched from the Arctic to the Gulf of Mexico, a warm, shallow corridor filled with marine reptiles, ammonites, and shoals of fish that drifted through gentle currents. The mega-tsunami roars into this seaway like a blade, slicing the corridor in two. In minutes, the wave pushes northward with such force that it dredges the sea floor, lifting sediments and chalk layers that had lain undisturbed for ages. Fossils found today in the seaway deposits show chaotic mixes of deep sea and coastal species packed together, a signature of violent transport. Marine life stands no chance. Mosasaurs, the apex predators of these waters, are not defeated by competition or scarcity but by physics. The wave is not something they can outswim. It carries them with it, twisting their bodies into debris fields that settle only when the water finally withdraws. Ammonites, delicate masters of buoyancy, shatter as they are thrown inland. Fish are lifted from their world and cast onto land where their bodies become trapped in sediments. Coral reefs, once thriving along the warm seaway, break apart into rubble. In some locations, these broken pieces later serve as foundations for new ecosystems, but on this day they are merely fragments of a vanished world. One remarkable feature of the impact tsunami is its echoing nature. Waves do not simply travel outward and fade. They collide with coastlines, rebound, interfere with one another, and create secondary waves. Along the margins of the Gulf, this interference produces chaotic patterns of rising and falling water that last for hours. Some waves arrive from the impact itself, others return after bouncing off distant shores. The result is a churning, unpredictable surface where no stable rhythm emerges. Geological evidence from sites near what is now Texas suggests repeated deposits of sand and silt, layered one atop another, each representing a separate pulse of water striking the land. Beyond North America, other continents feel the waves on gentler but still significant scales. The eastern shores of South America face seas that rise and fall with strange, unnatural patterns. Africa experiences coastal disturbances that leave behind layers of disturbed sediment. Even far-off Europe and Asia may have seen elevated water levels and odd currents. These are not the towering walls of water found near the impact, but they are reminders that the oceans are a single connected body, and when one part of that body is violently disturbed, the entire system responds. What makes this mega tsunami unique in Earth's history is the combination of speed, height, and origin. Earthquakes trigger tsunamis when fault lines shift. Landslides create waves when masses of debris fall into water. But this one began when the crust itself was removed. It was not triggered by a motion of land, but by the absence of land. The ocean rushed into a void, and then the void rebounded with force. Some researchers describe this as the ocean being punched from below, a description that, while metaphorical, aligns with the physics of the event. Sediment cores taken from the Gulf of Mexico record chaotic layers of material deposited in rapid succession. Some of these layers contain tiny glass spherules, formed when rock was vaporized and then rained back into the sea before being swept into tsunami deposits. Others contain shocked minerals transported from deep beneath the impact site. Beneath these layers lie older sediments, undisturbed by the violence. Above them lie younger deposits that mask the most direct evidence. But by drilling through them, scientists have pieced together a picture of a disaster so vast that its fingerprints span continents. Marine organisms preserved in the fossil record tell a quiet version of the story. Microfossils known as foraminifera, once abundant in the seaway, nearly vanish from the layers immediately above the tsunami deposits. Their shells show signs of rapid burial, mixed with sediment churned from different depths. Some are broken, some are pristine. Together they reveal a sudden, violent disturbance followed by relative calm as the waves dissipated. Even with all this evidence, our reconstructions carry uncertainty. The heights of the waves near the impact remain estimates based on models. The exact speed of propagation depends on water depth, geography, and the distribution of energy. Different studies produce different numbers, though all agree on the scale. This was one of the largest tsunami events in the history of Earth. But the details, like much of ancient geology, remain hidden behind time. As the waves travel outward, they gradually lose coherence. Far from the impact site, they become broad swells. Instead of walls, they are long, low rises in the sea surface, detectable mainly by how they disturb sediments as they move across shallow waters. These distant waves cause damage, but not as dramatically as those near the epicenter. Their power is spent slowly, dissipating across the world over hours, perhaps days. When the last of the waves passes and the oceans begin to settle, the seafloor bears scars that will remain for millions of years. Channels cut into the continental shelf remain visible in seismic imaging. Sediment layers show the chaotic nature of deposition. Coral debris fields mark the places where reefs were torn apart. The ocean, which once provided stability for countless species, has become a recorder of catastrophe. This is the first global wave, the pulse of water born directly from the Earth's sudden wound. It is not the final consequence of the impact, nor the most enduring, but it is the moment when the oceans rise higher than mountains, not in metaphor but in fact. It shows us how fragile coastlines can be when faced with the raw power of displaced water, and how interconnected the seas truly are. And it reminds us that even the largest bodies of water on Earth can be reshaped in minutes when the planet encounters something far older and far colder than itself. Imagine this, standing beneath a sky that begins to glow not because the sun is rising or setting, but because something far worse is happening above you. A faint shimmer at first, then a growing brilliance, until the entire dome of the atmosphere warms like the inside of a furnace. No flame you can see, no smoke at ground level yet, just heat falling from above as if the air itself has caught fire. Can the sky burn? Not in the way a forest burns, but in the way metal glows when pulled from a forge. And in the first hour after the Chicxulub impact, this is precisely what the atmosphere becomes. To understand how this happens, we must leave the ground and rise high into the sky, where thousands of tons of material thrown from the crater now arc along ballistic paths. In the first seconds after the asteroid struck, the impact excavated not just a crater, but a plume of molten rock, pulverized minerals, and vaporized crust that shot upward faster than most modern rockets. Some of this material escapes Earth entirely, flung past the atmosphere and into temporary solar orbits. But the vast majority follows graceful, deadly curves that will carry it around the world and back down through the atmosphere. This returning material is called ejecta. It is not uniform. Some fragments are large, jagged pieces of crust. Others are droplets of molten rock that cooled into tiny spheres, spherules, while still airborne. Even smaller grains contain shocked quartz, a mineral transformed under pressures so intense that its internal structure realigns. All of it is falling, and all of it, as it re-enters the atmosphere, begins to heat. The physics of re-entry heating are both simple and terrifying. When objects fall from space, they meet air at enormous speeds. Air cannot move aside fast enough, so it compresses and then heats. The falling object glows. It is the same phenomenon that ignites meteors each night, except here the number of falling objects is not measured in dozens, but in trillions. Every grain of dust, every bead of molten glass, every shard of rock becomes a tiny fireball. And together they fill the sky with more heat than any natural process on Earth can match. The glow begins quietly. High above the ground, the re-entering spherules heat the upper atmosphere. If you were standing anywhere in the northern hemisphere, you might see faint streaks of light, like shooting stars multiplied 1,000,000 times. But this is not a meteor shower. It is the sky returning pieces of the planet to itself. As the minutes pass, the streaks intensify. They multiply. They begin to overlap. Instead of lines, the sky becomes a curtain of brightness, each streak adding its own momentary heat to the ever-growing dome of radiance. The air warms rapidly, first by a few degrees, then by dozens. Scientists who model this moment describe the atmosphere as entering a state of thermal runaway, where the accumulation of radiative heat from falling ejecta raises temperatures across continents. It is not uniform. Some areas heat faster than others. The regions closest to the impact experience the earliest warming. But soon the effect spreads globally, carried by air currents and the constant fall of material from above. If you were an animal on the surface, you would not see flames at first. There would be no fire racing through forests yet. Instead, you would feel the air becoming hotter. Leaves would begin to wilt. Resin inside trees might start to soften. The heat radiates downward like the opening of a giant oven door in the sky. The atmosphere glows faintly, lit from within by countless returning fragments. For creatures that rely on vision, this glow is confusing. It resembles twilight, except brighter, harsher, with no source that the eye can locate. As more ejecta falls, the temperature reaches levels that ignite dry vegetation directly. Grasses, shrubs, and leaf litter burst into flame under nothing more than radiant heat. This phenomenon, known as global ignition, is supported by evidence from charcoal layers found in regions across the northern hemisphere. These charred materials form a geological line marking the widespread burning of forests. They suggest that in many places the ground caught fire not from falling debris hitting it, but simply from being heated by the sky. The falling ejecta itself is not always visible once the atmosphere begins to glow. The brightness can overpower individual streaks. Instead, the sky appears as a continuous dome of light, flickering as heavier fragments break through and momentarily blaze brighter than the rest. Some spherules, still partially molten, fall to the ground where they cool into tiny glass beads. These beads have been found across the world, embedded in sediments from the end of the Cretaceous. They tell us that the fire in the sky was not localized. It was global. Marine environments are not spared. Ejecta falling over the oceans heats the water surface, creating bursts of steam. Plankton, the foundation of marine food webs, experiences thermal shock. Shallow seas along coastlines become dangerously warm. Coral structures that survived the mega tsunami suffer additional stress from this sudden atmospheric heating. In deeper waters, the penetration of heat is less severe, but surface ecosystems face catastrophic warming. Microfossils taken from marine sediments show disruptions consistent with rapid temperature increases in the first hours after the impact. The mechanics of re-entry heating rely on the sheer volume of material thrown into ballistic trajectories. Some estimates place the mass of ejecta returning to Earth at several trillion tons. When this much material falls through the atmosphere, the cumulative effect is extraordinary. Each grain may only release a tiny amount of heat, but multiplied across the entire sky, the heat is enough to raise temperatures on land to hundreds of degrees in some models. This is not the temperature of the air itself, but the radiant heat reaching the ground from above. Spherules re-entering the atmosphere are only one part of the story. Larger fragments, several meters across or more, streak downward as incandescent boulders. Many of these break apart high in the air, releasing showers of smaller pieces. The sound of their re-entry would not reach the ground until later, travelling slower than light and heat. For now there is only silence and glow. The silence is deceptive. It gives the appearance of calm while the world is undergoing a form of atmospheric combustion. Geologists studying the boundary layer from this event often remark on the presence of shocked quartz. These microscopic grains, altered by the impact, are found across continents. Their distribution shows us how far the plume reached and how widely the ejecta was spread. In North America, Europe, Asia, and beyond, tiny grains of quartz tell the same story. Material was thrown high into the atmosphere, circled the globe, and fell back with enough velocity to heat the air around it. The vegetation on land, already vulnerable to rising temperatures, now faces ignition from above. Pine needles, dry grasses, and brush catch fire easily. Moist leaves resist longer, but they too succumb as the temperature continues to rise. Flames begin to appear across landscapes simultaneously, with no central direction or obvious origin. It would look, to any creature watching, as if fire were emerging spontaneously from the ground in all directions. This is the moment when forests across entire continents ignite. The intensity of this global burning varies. In wetter regions, the moisture in the vegetation slows ignition. Some models suggest that tropical forests may have resisted the initial flare-up, though they would face other challenges in the hours that follow. But in drier or seasonally arid regions, the ignition is nearly instantaneous. Charcoal deposits in these areas are thicker, more chaotic, reflecting the turbulent nature of the fires. It is important to note that not all scientists agree on the exact intensity of these fires. Some propose that atmospheric heating alone was enough to ignite vegetation globally. Others suggest that only regions closer to the impact site experienced this effect, while more distant areas saw less direct burning. The debate continues, and this uncertainty reminds us that our reconstructions, while detailed, are not perfect. We rely on the evidence we have, knowing that much of the Earth's memory remains hidden beneath layers laid down long after the event. Still, even with these uncertainties, the broad picture is clear. The re-entry of Ejecta transformed the atmosphere into a radiant shell of heat. It was not fire in the ordinary sense, with flames leaping from fuel. It was radiative energy descending from millions of incandescent fragments streaking through the sky. It was light and heat acting together, overwhelming the world below. As the hour progresses, the rate of falling ejecta begins to slow. The brightest phase of the sky glow dims, the heat lessens though slowly. The fires burning on land continue independent of the sky's influence, but the atmosphere gradually cools from its unnatural radiance. The last glowing spherules fall to the ground, cooling into perfect glass beads that will one day be discovered and held in human hands. Their smooth surfaces will reflect laboratory lights instead of the fiery sky they were born into. Their presence will tell scientists that once, long ago, Earth experienced a rain of molten glass. For now, the sky remains warm, the air shimmering with heat. The world below is changed forever. The atmosphere is burned not with flame but with falling stars, each a piece of Earth returned by gravity. And when the last of the spherules falls, and the glow begins to fade, the world enters the next stage of the catastrophe. A world where fire is no longer a line creeping along the ground, no longer a storm that rises in a single forest or valley, but something far larger. Imagine looking to the horizon in any direction and seeing the same thing: flame. Not because lightning struck, not because trees were dry, but because the sky itself had delivered enough heat to ignite an entire planet almost at once. What does Earth look like when fire stops being local and becomes global? Hours after the impact, the radiative heating from falling ejecta has begun to ease, but its consequences have only just begun. Vegetation across the continents, already stressed by the intense atmospheric glow, now reaches ignition temperature in places that would ordinarily resist flame. Pine forests, savanna shrubs, fern-carpeted wetlands, and dry inland plains all begin to burn. Not all ignite at the same moment, and not all burn with equal violence. But enough do that. From a geological perspective, Earth becomes a planet of fire. To understand this transformation, we leave the immediate impact zone and move across continents where the evidence still lies in thin, dark layers of soot preserved in rocks. These layers, found in North America, Europe, Asia and beyond, form a global fingerprint of combustion. They contain carbonized plant fragments, microscopic flecks of charcoal, and soot particles generated only when organic material burns in high oxygen environments. These soot layers are not thick, they are measured in centimetres or even millimetres. But their distribution is astonishing. They appear in sediment cores from lakes, in marine deposits near coastlines, and even in deep ocean basins. Their near-simultaneous placement across geological records tells us that fires were not isolated incidents. They were global events. The mid to late Cretaceous world was rich in oxygen, more so than today. Estimates place atmospheric oxygen content at around 30%, compared to the 21% we breathe now. That extra oxygen made the world more flammable. Plants burned more readily, flames spread faster, embers remained hot for longer. Combined with the radiative heating from the re-entering spherules, the conditions for widespread ignition were perfect. In many regions, all that was needed was a final spark, and the sky provided not one spark, but trillions of tiny molten grains, falling like silent embers across the land. The earliest fires begin in regions where vegetation is driest. Inland plains, where seasonal droughts had already thinned moisture, ignite quickly. Pine forests release volatile resins, causing intense bursts of flame that leap rapidly from tree to tree. Ferns, ordinarily resistant to fire due to high water content, begin to wilt and then combust as radiant heat continues to warm the ground long after the ejecta glow has faded. Even wetlands are affected. Marsh vegetation dries at the surface, igniting in patches that then spread outward along peat-rich soils. These fires move slowly at first, but their breadth makes them impossible to contain. They merge into larger burn areas until entire ecosystems are engulfed. One of the most striking pieces of evidence for this global combustion comes from soot found in the boundary layers of marine sediments. The soot is fine, made of tiny carbon particles that can only form when organic material burns in open air. These particles travelled far from land, blown into the atmosphere and carried over oceans before settling into marine basins. Their presence tells us that fires burned long enough and hot enough to inject smoke into the upper atmosphere. But they also tell us something else, that the fires were widespread enough to produce soot on a global scale. This is something no modern wildfire system can achieve. Even the largest fires of the present day cannot generate soot that travels across hemispheres. But the fires of the late Cretaceous did. In some places the soot layer is mingled with microtectites, glass droplets formed from impact melt. This mingling suggests that fires began while ejecta was still falling, or shortly thereafter. It indicates that the two events overlapped in time. Radiative heating ignited the vegetation, and the falling spherules supplied additional heat while the fires raged. Together they created a world where flames spread not from a single source, but from countless points across the landscape. As the fires expand, the energy they release begins to influence the atmosphere itself. Large hot fires produce towering convection columns that can rise tens of kilometers into the sky. Some modern fires create their own weather, pyrocumulus clouds capable of generating lightning. It is reasonable to imagine that the vast fires of this ancient world produce similar effects, but here it is important to remain cautious. The geological record contains soot and charcoal, not detailed meteorological data. We cannot say with certainty that lightning storms formed above these ancient infernos, though the physics allow for it. The safest conclusion is that the fires were intense enough to send enormous quantities of smoke into the sky, altering atmospheric conditions across continents. The extent of these fires varies by region. In some areas, like parts of what is now North America, evidence suggests complete burn-through of forests. Charcoal fragments in these regions are abundant, indicating high-intensity fires capable of consuming entire ecosystems. In other regions, like certain tropical coastlines, the fires may have been patchier. Moisture content in tropical vegetation can resist ignition, even under extreme radiant heat. But even here, the unusual atmospheric conditions likely cause scattered fires. And even where the vegetation itself didn't burn completely, the smoke from distant fires would have drifted overhead, depositing soot and altering light levels. To imagine what Earth looked like during these hours, picture entire horizons glowing orange, not with the bright crackling flames of a modern wildfire, but with a deep continuous burn stretching across landscapes. Toward the coastlines, smoke rises like low, dark pillars, merging into a continuous grey layer as it drifts across the sky. Inland, the glow reflects off clouds, turning them a muted, smouldering red. The ground beneath the fires is charred and cracked. Resin bubbles burst on tree trunks. Ferns collapse into ash. Forest floors, once thick with leaf litter and undergrowth, become blankets of charcoal. One of the most humbling pieces of evidence for these fires lies in isotopic signatures within the boundary layer. Certain carbon isotopes shift in predictable ways when organic material burns. These isotopic ratios provide a chemical record of combustion, even when visible charcoal is absent. They tell us that a significant fraction of the world's biomass burned within a short window of time. Not necessarily everywhere, but in enough places to leave a unified chemical fingerprint across continents. Scientists debate whether these fires were truly global or merely widespread. Some models argue that moist regions may have escaped the worst of the burning. Others suggest that even these regions experienced heat stress and partial ignition. The diversity of modern ecosystems makes it tempting to assume that some areas of the ancient world were less affected, but the geological record shows a remarkably consistent layer of soot, hinting that the scale of burning exceeded anything Earth has experienced before or since. Marine evidence supports this idea. Soot particles found in deep sea cores are often mixed with other combustion products, such as polycyclic aromatic hydrocarbons, which form during incomplete burning of organic material. Their presence suggests not only widespread fire, but fire intense enough to generate complex organic aerosols. These aerosols would have drifted through the atmosphere, eventually settling over oceans and sinking to the seafloor, where they became part of the geological archive. As the hours pass, the fires continue to spread. Some follow the patterns of prevailing winds, moving east or west depending on continental geography. Others follow the topography of the land, flowing upslope when wind-driven, or down into valleys when convection currents dominate. The fires do not all merge into a single continuous burn, but their combined effect is planetary in scale. In many places, ash begins to fall like snow, accumulating on surfaces and smothering smaller flames. One of the subtler consequences of these fires is the change in ambient light. Even as the flames burn brightly, the smoke above them dims the sun, creating a shifting palette of reds, oranges, and browns. The world becomes visually muted, as if viewed through a layer of tinted glass. The air grows thick with particulate matter. In some regions, this haze may have reduced visibility to just a few meters, yet the fires still advance, feeding on the oxygen-rich atmosphere and the dry, heated vegetation. Eventually, the radiant heat from the sky diminishes as the rate of falling ejecta decreases. But by then, the fires on the ground have become self-sustaining. They no longer need the sky's heat to move. They rely on fuel, forests, grasslands, brushlands, peat beds. And there is more than enough fuel to burn. This is the moment when Earth transitions fully into a planet of flame. It is a world reshaped by combustion, marked by the disappearance of entire ecosystems and the creation of new mineral and chemical signatures that will persist in the rock record for tens of millions of years. When the fires finally die down, their ashes will settle into a thin, dark line that future geologists will call the boundary between eras. But for now, the world burns quietly, relentlessly, under a sky that has already delivered the worst it had to offer. Waking to a world where morning arrives, but light does not. The sky brightens faintly, only to settle into a permanent twilight that never deepens, never lifts. Shadows blur into the air. Colours flatten. The sun becomes a pale disk, struggling behind a ceiling of dust. And for the first time in tens of millions of years, Earth forgets how to let daylight through. What happens to a planet when its atmosphere stops being transparent In the days following the impact, the fires still burn in many regions, but another force is already gathering far above them, silent and indifferent. The same explosion that carved a crater into the Yucatan launched billions of tons of dust, ash, pulverized rock, sulfur particles, and microscopic droplets of molten minerals into the upper atmosphere. Some of these particles rose on thermal plumes created by the fires themselves, while others were thrust high enough to reach the stratosphere in the first seconds of the event. Once there, they entered a realm of air so stable and so slow to mix that anything carried into it can linger for years. The transformation begins gradually. At first, the sky dims only slightly. The sunlight reaching the surface is filtered, softened, as if passing through a permanent haze. But as more particles spread, drifting along global circulation patterns, the dimming intensifies. Within days, the clarity of the sky is gone. The blue fractures into muted grey. The horizon becomes a band of ochre dust. The sun, once bright enough to cast defined shadows, now appears as a faint halo that offers no warmth. The particles responsible for this dimming vary widely in size and composition. Some are fine silicates, the pulverized remains of the seabed and limestone platforms that once lay beneath the impact. Others are microscopic droplets of glass formed from molten ejecta that cooled mid-air. Sulfate aerosols, formed when vaporized sulfur from the Yucatan's gypsum-rich rocks reacted with water in the upper atmosphere, play an especially potent role. These aerosols scatter sunlight with remarkable efficiency, reflecting a portion of incoming energy back into space. Their presence alone can drive significant cooling, but combined with dust, soot, and ash, their effect becomes profound. The atmosphere becomes layered with particles, each type drifting at different altitudes. Fine dust settles slowly, remaining aloft for months. Soot particles from global fires mix into these layers, darkening them further. The stratospheric sulfate aerosols persist longest, stable in the cold, calm air above weather systems. Together they create a planetary veil that tightens around the world, absorbing and deflecting light before it reaches the ground. As sunlight weakens, surface temperatures begin to fall. This cooling is not subtle, it is sharp, rapid, and widespread. Regions once warmed by tropical or subtropical climates drop toward freezing. Nights grow colder still, reaching temperatures not seen since earlier geological eras. Even areas that normally fluctuate within warm ranges begin to experience frost. The Earth enters what scientists call an impact winter, though the term hardly captures the abruptness of this shift. Models suggest that temperatures in some regions could have dropped by 20 degrees Celsius or more in a matter of weeks. The exact magnitude varies based on geography, ocean currents, and local atmospheric composition. But the trend is clear. A planet that once thrived under greenhouse conditions, with lush forests and warm shallow seas, now cools under an endless grey sky. This cooling does not rely on seasonal shifts. It spreads across latitudes, affecting equatorial regions almost as strongly as temperate ones. One of the earliest and most profound consequences of this dimming is the collapse of photosynthesis. Plants rely on light to convert carbon dioxide into organic matter. Without sufficient light, this process slows and then stops. In the oceans, phytoplankton, tiny organisms that form the base of marine food webs, begin to die as light fails to penetrate the surface layers. The upper ocean turns darker. The greenish tint of productive waters fades into dull, brownish hues. Some phytoplankton can survive on extremely low light levels, but only for a time. Their decline marks the beginning of a cascade that will affect entire ecosystems, though we will not follow those consequences here. On land, the remaining vegetation, already stressed by fires and heat, begins to respond to the lack of sunlight. Leaves droop, cells weaken, growth halts. Trees that survive the fires stand like silent pillars, their metabolic processes slowed to near stasis. Ferns attempt to unfurl but fail. Seedlings that might have taken advantage of freshly cleared land find no energy to grow. In forest understories, darkness becomes nearly absolute. Even midday resembles late evening. As temperatures continue to fall, atmospheric moisture begins to condense. Clouds form more frequently, and precipitation increases in some areas. But this rainfall carries something new: acidity. When sulfur aerosols mix with water in the atmosphere, they create sulfuric acid. Rainfall becomes mildly acidic, enough to stress certain plant species and alter soil chemistry. Lakes and streams acidify. In some regions, acid deposition strips nutrients from soils, interrupting cycles that once sustained rich ecosystems. This is not an acid rain catastrophe in the modern sense, but it is a significant shift in environmental chemistry that compounds the stresses already facing the biosphere. In the oceans, cooling temperatures affect surface layers rapidly. Cold water sinks, disrupting thermal gradients. Circulation patterns shift. Upwelling zones, which bring nutrient-rich water to the surface, falter. Some studies suggest that ocean turnover during this period may have been unusually vigorous, as cold water pushed downward, altering deep-sea chemistry. But much of this remains uncertain. We can trace carbon isotopes, microfossil distributions, and chemical signatures, yet the exact sequence of oceanic changes still carries debates. What is certain is that light-dependent processes faltered long before chemical or thermal changes reached their full extent. The dust veil thickens over time. Larger particles fall first, settling across continents and ocean surfaces. These deposits contain minerals that can be traced back to the impact site or to fires ignited by the re-entry heating. But the fine particles, especially sulfates, remain aloft. These are the particles that create the most pronounced dimming, reflecting sunlight outward. Their persistence explains why the cooling lasts not for weeks alone, but for months, perhaps years. The scale of this dimming becomes especially clear when we consider the brightness of the sun at the surface. Under normal conditions, sunlight delivers a certain amount of energy measured in watts per square metre. During the impact winter, this energy flux drops sharply. Light becomes diffuse. Even at midday, the intensity resembles nothing more than a heavy overcast day. Plants accustomed to full-spectrum sunlight struggle. The warmth that normally radiates through forests or across plains diminishes. Animals that rely on visual cues find the world washed in grey. In this muted environment, the boundaries between day and night blur. Dawn and dusk stretch across hours. Noon brings only a slight increase in brightness. Shadows soften into vague outlines. Colours fade. The world becomes monochrome, not through snow or ice, but through the density of dust and aerosols that linger in the air. One of the most humbling aspects of this phase is how global it is. The dimming does not stop at coastlines or mountain ranges. It travels with the winds, covering continents and oceans alike. The stratospheric aerosols drift slowly along the equator before spreading toward the poles. This slow expansion creates a world where no region remains untouched. Even the high latitudes, already prone to long periods of low light, experience further dimming that pushes them into extended cold. Ice begins to form in places that rarely saw frost. Soil hardens. Lakes freeze earlier than normal. In coastal regions, shallow waters cool enough to change local currents. The planet becomes a colder version of itself, wrapped in a veil that has no intention of lifting soon. And yet, amidst all this, we must acknowledge uncertainty. Estimates of how long the dust winter lasted vary. Some models suggest several years of extreme dimming followed by gradual improvement. Others propose a shorter peak accompanied by a longer tail of cooling. The geological record gives us snapshots, not full stories. Soot layers, microfossils, isotope curves, each provides a fragment. Together they build a picture of profound cooling and darkness, but the exact timeline remains an area of scientific exploration. What is clear is that Earth entered a state of forced dormancy. The sky forgot how to transmit light. The surface forgot the warmth of sunlit mornings. The air grew colder, heavier, darker. And in that darkness, ecosystems that had thrived for millions of years faltered. This is the moment when the planet held its breath. A world that once shimmered with sunlight and colour now sat beneath a grey, unmoving sky, waiting for the first signs that light might return. Imagine this, the last giants walking through a world that no longer remembers how to feed them. Creatures built for warmth now stepping across frozen ground. Bodies evolved to graze through endless forests, moving through landscapes where the leaves never grew back. What does it feel like for a lineage that ruled Earth for tens of millions of years to meet a world it was never designed to survive? Months after the impact, the dust-choked sky has dimmed the sun to a cold, distant memory. Days remain grey. Nights stretch longer than any season the dinosaurs ever knew. The forests they depended on are gone, burned or wilted or buried beneath ash. Plains that once shimmered with cycads, ferns and flowering shrubs now stand barren, their soils hardened by frost. Rivers run shallow, slowed by cold and clogged with debris. The greenhouse world that sustained giant bodies has vanished, replaced by an air that bites the skin and ground that offers almost nothing to eat. The first to feel the strain are the herbivores. For creatures built around constant feeding, the collapse of plant life is immediate and absolute. Hadrosaurs, once abundant in northern floodplains, wander across dead landscapes in search of edible matter. Their jaws, engineered for grinding tough leaves, now meet only sticks, charred bark, or frozen stems. Bone beds from the very end of the Cretaceous tell the story with uncomfortable clarity. Clusters of individuals preserved together, many showing signs of malnutrition in their last growth rings. In these rings, called lines of arrested growth, bone deposition slows to a halt, a biological handwriting of famine. Sauropods, where they still roamed, face an even harder fate. Their massive bodies require an ecosystem rich in high biomass plants, something the impact winter strips away completely. In regions where their fossils vanish abruptly, the absence of young individuals in late Cretaceous strata suggests reproductive collapse. No hatchlings, no juveniles, a population aging toward zero. Paleontologists studying these deposits do not find evidence of sudden mass death alone, but something more drawn out, slow starvation across generations. Predators suffer next. Tyrannosaurus, apex hunter of the Northern Hemisphere, is not defeated by any rival. It is undone by emptiness. As herbivore numbers plummet, so do the carcasses that sustain scavengers and hunters alike. Some fossils show stress lines in teeth, indications of poor nutrition in the animal's final months. Others reveal thinning bone walls, a sign that even top predators faced prolonged hunger. In the last sediments before their disappearance, tyrannosaur remains become fewer, scattered and isolated. Ecological modelling helps explain why. The collapse of prey pushes large-bodied predators into extinction even faster than the herbivores they depend on. Smaller carnivores fare little better. Dromaeosaurs and other mid-sized hunters, which once thrived on diverse prey, encounter the same barren world. The once vibrant ecosystems of coastal plains, forests and swamps now offer little more than frozen soil, fallen trunks, and the remnants of species already starving. Tracks that were once common in sedimentary layers become rare, diversity crashes, and with each passing season, the skeletal record shows fewer signs of growing juveniles. Bone histology gives us one of the clearest windows into this decline. Under a microscope, dinosaur bones reveal rings much like trees. In normal years, these rings vary with seasons, fast summer growth, slower winter deposition. But as the impact winter deepens, these cycles break. Growth becomes irregular, interrupted by periods of malnutrition. The lines of arrested growth, dense, dark bands, appear closer together, signalling repeated cycles of scarcity. In some specimens from the period immediately before the Cretaceous ends, growth stops almost entirely. These bones speak softly, but they say enough. The giants were starving. Environmental evidence complements this. Plant fossils from the final stretch of the Cretaceous disappear from many regions. Pollen, once abundant in sediments, thins dramatically. Charcoal persists, but new growth does not. This tells us that even in regions spared the worst fires, photosynthesis had halted. With the sun dimmed by dust and sulfate aerosols, plants could not recover. Even hardy species experienced die-offs. Spores from ferns, which normally surge after disturbances, do appear, but without sufficient light, even they fail to rebuild ecosystems quickly. And without plants, the animals that depended on them simply could not endure. The oceans too show signs of stress, though we focus here on land dwellers. Marine die-offs eliminate coastal feeding grounds for species that occasionally relied on shoreline scavenging. Inland, colder temperatures and altered hydrology change river patterns. Floodplain habitats shrink. Wetlands freeze. Areas once rich in edible plants become sterile. Bone beds in these former wetlands preserve mixed assemblages of herbivores and carnivores that likely died near dwindling water sources, drawn together not by ecology, but by desperation. Climate models give us a sense of how rapidly this cooling occurred. With sunlight reduced and aerosols lingering in the stratosphere, temperatures could drop by tens of degrees. Large-bodied animals like ceratopsians and titanosaurs are adapted to warmth. Cold stresses their metabolism. In freezing conditions, body heat becomes a currency they cannot conserve. Fossil evidence of cold stress is not directly visible in bones, but the disappearance of species from northern latitudes before they vanish entirely suggests a southward retreat. Yet even migration offers no refuge. The cooling is global, no latitude escapes. Fossil distributions show no safe havens, no geographic pockets where dinosaurs persist significantly longer than elsewhere. Their decline is continent-wide. Predators face an additional problem. The collapse of prey density leads to greater competition and potentially lethal encounters among remaining individuals. Tooth-marked bones from the very end of the Cretaceous hint at desperate scavenging. Some fossils show multiple carnivore bite marks, suggesting repeated feeding attempts on dwindling carcasses. These behaviours are normal in predators, but their increase during this period fits with a world running out of food. Juveniles are the most vulnerable. Their growth requires significant energy. Bone evidence from late-stage fossil sites often lacks young individuals entirely. Hatchling remains become scarce. This absence signals a population unable to reproduce or rear young in the face of resource collapse. A species without juveniles has already begun to end, even before the last adult falls. To visualize this world, imagine herds of once mighty herbivores moving across empty landscapes, snow-like ash drifting around them. Their calls echo across plains that no longer answer with the life. Trees stand leafless and skeletal, their branches blackened. The chill in the air deepens each month. Rivers freeze along their edges, marshes harden into brittle crusts. The world that shaped dinosaur evolution for millions of years disappears faster than their bodies can adapt. There is no dramatic last stand, no single event to mark their passing, just a long, quiet dwindling. Fossils from the very last layers of the Cretaceous show fewer species, fewer individuals, fewer footprints, fewer signs of life. In some places, the last dinosaurs are represented by scattered bone fragments, worn and thin, suggesting weakened animals. In others, they appear as isolated skeletons, not part of herds or packs, but alone, another sign of ecosystem collapse. The disappearance of the dinosaurs is often described as sudden, but the skeletal record suggests something more sombre, a prolonged struggle against a world fundamentally altered. The cold, the hunger, the darkness, each played a role. Ecological networks that once supported massive herbivores and apex predators unravelled piece by piece. With plants gone, herbivores starved. Without herbivores, predators starved. Without sunlight, both lacked the basic resources needed to recover. And yet, even here, uncertainty remains. Estimates of how long dinosaurs persisted after the impact vary by region. Some evidence hints at pockets surviving for months or possibly a few years. Other studies argue for a more rapid disappearance. The fossil record is partial, incomplete, a scattered puzzle. But the broad picture is consistent. The giants that once defined the Cretaceous faced a new world they were not built to endure, and their decline was not a single moment but a slow unravelling of life at the top of a collapsing food chain. In this twilight of the dinosaurs, the earth grows quiet. The last giants step across frozen ground that remembers the forest that once stood there, and with every passing season, their footprints become fewer until the world no longer feels their weight. Imagine standing beside an ocean that no longer knows how to breathe. Not storming, not heaving, not roaring with the ancient pulse that once shaped continents, but simply resting under a stillness so complete it feels unnatural. For millions of years, the seas were the engine of the life on this planet. In the last years of the Cretaceous, they were warm, nutrient-rich, crowded with creatures that had conquered every depth. But after the impact, they entered a phase of transformation so severe that even the land's devastation seemed, in comparison, almost brief. What happened beneath those darkened waves was a slower, colder ending, one that unfolded long after the fires on land had burned themselves out. To understand why the oceans suffered longer, begin with the smallest architect of their stability. The plankton that drifted in the sunlit surface, capturing light, turning it into carbon, and feeding almost everything that swam below. In the first weeks after the asteroid, sunlight faded behind a global veil of dust and aerosols. On land, darkness brought cold. In the oceans, darkness brought something worse, starvation at the level of molecules. Without sunlight, photosynthesis stopped. Without photosynthesis, the microscopic algae that formed the base of marine food chains began to die. Not all at once, but in cascading waves that rippled across entire basins. Shock layers preserved in deep-sea sediments show the disappearance of foraminifera, tiny shelled organisms whose fossils now dominate the geological archive. Before the impact, their species diversity was astonishing. Afterward, the fossil record narrows into silence, thinned to a handful of survivors living in conditions they had never evolved for. These creatures depended on warm, transparent water and stable chemistry. The impact had erased all three. As the skies filled with dust, the upper layers of the ocean dimmed to a green-brown murk. Within months, water temperatures began to plummet. Sun-driven circulation slowed. Seasonal mixing faltered. The seas became stratified, as if layers of history were refusing to blend. acid rain formed from sulfate aerosols released when the asteroid struck sulfur-rich rock, washed into the oceans, lowering pH across entire coastlines. In normal conditions, the ocean's natural buffering would have stabilized things, but nothing was normal now. With photosynthesis halted and carbon cycling broken, carbonate ions that once built shells were suddenly scarce. Marine organisms that relied on them, ammonites, planktonic forams, some coral species, found the water subtly hostile. Their shells began dissolving. Their larvae failed to mature. Their food vanished. For millions of years they had adapted to environmental changes, but not to the sudden collapse of their chemical foundations. In the coastal shallows, reefs that had once burst with colour began to bleach. The word bleach may feel modern, but the process is ancient. A coral expels its symbiotic algae when stressed, losing its main source of energy. With sunlight gone and the water chilled, these algae could not survive. Reefs dimmed. They did not die all at once, but slowly, like cities losing their citizens one by one. Many of the animals that depended on them, reef-dwelling fish, crustaceans, small marine reptiles, disappeared long before the cold reached its peak. Farther out, in the open ocean, large predators such as mosasaurs and plesiosaurs faced a different kind of crisis. They were built for abundance, fast metabolism, large bodies, complex hunting behaviour. But when their prey species declined, their world narrowed. A predator can survive temporary scarcity, but not years of it. Bone beds from the very end of the Cretaceous show fewer juveniles, fewer subadults, than none at all. It is a quiet pattern, almost gentle in the fossil record, but its meaning is irreversible. A lineage with a limited reproductive window cannot withstand a collapse in food supply. Sometimes we imagine extinction as sudden, dramatic, an animal taking its last breath in a moment of catastrophe. The ocean tells a different story. It suggests disappearance through thinning, fewer individuals each year, fewer nests, fewer shells, until a species becomes rare enough for chance to finish what the climate began. These seas after the impact were not instantly lifeless. They were simply changed into a system that no longer supported the complexity of the late Cretaceous, and the creatures that depended on that complexity faded as the system simplified. Geologists studying the boundary sediments often comment on the unusual thickness of clay rich in iridium and altered glass, but they also note layers of fine, homogeneous mud that reflect decades of near motionless water above. When plankton die, they sink. When they sink in enormous quantities, they create a rain of carbon that deoxygenates deeper layers. It appears this occurred repeatedly during the first years after the impact. In many parts of the world, bottom waters turned hostile to life. Bacteria that thrive without oxygen flourished in their place, releasing gases that altered local chemistry even further. The larger marine reptiles, already stressed, likely faced two bottlenecks at once: dwindling prey above and rising toxicity below. Imagine the choices they faced, if one can even speak of choice at such scales. To swim through colder water with less energy, to descend into deeper zones where oxygen was vanishing, to navigate a world where every migration route had become a corridor of scarcity. The foraminifera tell us much of what happened. The absence of mosasaur bone beds after the boundary tells us the rest. What makes the marine collapse especially striking is the asymmetry between land and sea. On land, after the fires and darkness, new growth would eventually return. Plants can remain dormant, seeds can wait. Soil can preserve life in forms that look inert but are merely resting. In the oceans, there is no true dormancy for phytoplankton. They require light. When light failed for months, the system lost its ability to reset. When light returned, It was weak and filtered through a haze of dust and ash still settling from the upper atmosphere. Recovery was possible, but slow. Too slow for creatures that lived on the edge of metabolic limits. Some paleontologists suggest that marine life took not years but decades to reach a new equilibrium. That word, equilibrium, may sound calm, but its implications are profound. It means the oceans did not return to their former state. They became something simpler, colder, and more suited to the organisms that would later rise in the Paleogene. The age of giant marine reptiles ended quietly, written not in a single violent moment but in thousands of days of diminished sunlight and altered chemistry. It is tempting to think of the ocean as immune to events on land, as if its depth provides a buffer against the world above. Yet the boundary layer shows the opposite. The seas were just as vulnerable, perhaps even more so. When sunlight dims, the top layers lose energy. When they lose energy, circulation slows. When circulation slows, nutrients sink out of reach. In a sense, the upper ocean became a starving, stagnant lid over a deep world that could not compensate. As sediments accumulated over the next few decades, they captured the story with remarkable clarity. The sudden vanishing of species that had flourished for millions of years, the shift in carbon isotope ratios reflecting a disrupted food chain, the appearance of new forms that evolved to exploit the simplified ecosystem. The seas did recover, but only after the extinction had already run its course. By the time sunlight fully returned, much of the marine world that had defined the Cretaceous was gone. What remains today from that period are subtle traces in limestone cliffs, microfossils in ocean cores, and the shape of the evolutionary tree that grew from what survived. The silence that followed the impact was not empty. It was full of chemical signals, slow cooling, and the quiet restructuring of the planet's largest biome. If you were to stand on a cliff overlooking those oceans, in the first years after the impact, you would not see a dead world. You would see one adjusting painfully to the new rules written in the sky. And in that adjustment lies one of the most enduring lessons of Earth's history. Life does not end easily, but it does transform completely when the conditions that shaped it collapse. As a humble observer, I can only piece together these details from cores, fossils, and the modelling done by researchers far wiser than me. What we know is limited but sufficient. The ocean suffered longer because its foundation was built on light, chemistry, and stability, and all three disappeared. The land burned quickly, the seas faded slowly, both changed forever. What if I told you that sometimes survival is not about strength, or teeth, or speed, but about knowing how to disappear? In the years after the impact, when the fires dimmed and the ocean still held their breath, the surface of the earth became a landscape where size was a liability. The giants struggled in the open. The medium creatures faltered in the cold, but in the soil, beneath the ash and frost, something else persisted. Small bodies that had learned long before the asteroid arrived that safety was not found in sunlight, but in darkness. Imagine the ground itself as a layered refuge. Inches below the surface, where the heat of the global firestorm no longer reached, mammals found pockets of stability. Not comfort. Nothing about these years resembled comfort, but consistency. And in a world disrupted from atmosphere to ocean floor, consistency was rare. Paleontologists studying these early mammals often remark that their survival was not miraculous. It was practical. They already possessed the behaviours required to outlast catastrophe. Burrowing species had existed for tens of millions of years by the time the sky changed. They knew how to live unseen. The first years after the impact were marked by a kind of cold that arrived too quickly for large animals to adapt. But small mammals, with high metabolic rates and flexible diets, had a way of meeting cold on its own terms. They slowed themselves down. Many of them entered states of torpor, reducing their body temperature and energy needs. This ability is ancient. We see hints of it in bone histology, in the growth lines that resemble tree rings, in the physiology of their modern descendants. These early survivors could switch between activity and near-suspended animation faster than larger creatures could adjust to even minor temperature drops. Their bodies were built for fluctuation. Fur gave insulation. Small size allowed quicker warming when they emerged. High reproductive rates meant that even in dire conditions, a few litters could offset losses. Most importantly, their diets were not restricted. When the forests above froze and the last green plants vanished beneath ice and soot, mammals could feed on seeds, roots, fungi, insects, carrion, anything with calories still locked inside. In a world where specialization had once been an advantage, generalists suddenly inherited the night. In many places, evidence of burrows preserved in Cretaceous and early Paleogene sediments hints that mammals either dug deeper or moved into pre-existing cavities. Soil collapses around fossilized dens show the diameter of tunnels once maintained by creatures no larger than modern mice or shrews. These tunnels provided shelter from temperature extremes and from airborne chemicals that settled after the impact. Ash, acidic mist, and particles of pulverized rock. Deep within the earth, air became filtered by layers of soil. Water seeped through in threads, cold but drinkable. It was not pleasant, but it was survivable. Some mammals likely maintained networks of burrows shared by several individuals. We cannot know their social habits in detail, but comparisons with modern analogues suggest that communal warmth may have been a powerful advantage. Small animals pressed together lose heat more slowly, and huddling reduces the energy needed to stay alive during long periods of scarcity. These burrow systems were not homes in the sense we imagine, but temporary refuges where life compressed itself into a narrow margin, waiting for the world above to settle. While the surface froze and thawed unpredictably, food in the soil remained relatively stable. Roots do not vanish instantly. Insect larvae buried in rotting wood continued their life cycles. Fungi grew in decaying plant matter even without sunlight. Early mammals were not picky. Their teeth, as shown in wear patterns on fossil mandibles, were suited for grinding, slicing, and gnawing. They could shift from seeds one season to worms the next. Flexibility became a survival strategy as potent as claws or speed. It is easy to imagine these creatures as desperate, but the fossil record suggests something quieter. Not triumph, not dominance, just persistence. A lineage accustomed to shadows continuing its routines while the world above roared and fell quiet. Their skeletons do not show sudden changes that would imply panic or dramatic evolutionary leaps. Instead, they display continuity, bodies already adapted to marginal environments simply following the behaviors they had practiced for ages. In this sense, the mammals did not rise because the dinosaurs fell. They survived because their lives required less of the world in the first place. Some species may have used torpor in more extreme forms. In modern mammals, hibernation is a highly refined version of torpor, but its evolutionary roots are older. The ability to depress metabolism, slow the heart, reduce oxygen consumption, and remain motionless for days or weeks would have been invaluable in a period when emerging from a burrow meant entering air that could kill in minutes. Geological evidence of early Paleogene temperature fluctuations suggests winters that lasted several years. A creature that could sleep through much of that would avoid dangers without needing to confront them. Other mammals survived by foraging at night, when temperatures were more stable. Night activity was not new for them. In fact, many mammalian lineages evolved in the shadows of dinosaurs and had already developed adaptations for nocturnal living. Sensitive hearing, acute sense of smell, whiskers that served as tactile sensors in the dark. When the sky dimmed after the impact, the world became one long twilight. For dinosaurs, twilight was disorienting. For mammals, it was familiar. Burrow fossils found in what is now Montana show branching tunnels that end in large chambers, possible nests. Inside these chambers, researchers have found plant fragments, tiny bones, and traces of bedding material. These remnants suggest early mammals created pockets of warmth using dried vegetation or shredded fibers. In the aftermath of the impact, these nests may have been critical microenvironments, keeping offspring alive under conditions that would have killed them in the open. Some mammals likely travelled between burrows, taking advantage of temporary thaws when the dust-thickened sky allowed slightly warmer temperatures. They were not migrating in the way large animals do. Instead, they moved cautiously from one patch of edible matter to another. Their range was small, their steps measured. Every surface was coated with ash. Every breath carried particles, but small bodies breathe shallowly. They can use microhabitats as tiny as a patch of moss or a layer of fallen needles. Their world, though damaged, was still navigable. One of the most important advantages mammals possessed was reproductive strategy. Unlike many reptiles of the time, which laid eggs vulnerable to temperature swings, mammals kept developing young within their bodies. Gestation protected embryos from external cold. Nursing provided food even when plants had disappeared. This internal system, warm, controlled, flexible, may have given mammals a buffer against the collapse of food chains around them. Evidence from tooth eruption patterns in fossil jaws indicates relatively short maturation times, which meant offspring reached independence quickly and did not require large stores of energy to raise. The world they inherited was not kinder than the one before. It was simply emptier. As months turned into years and the skies remained dim, the mammals continued their quiet routines. Dig, feed, rest, emerge, forage, retreat. No single adaptation explains their survival. It was the combination of smallness, flexibility, temperature resilience, and behavioral conservatism. They did not need lush forests, abundant prey, or stable seasons. They needed only pockets of shelter, scraps of food, and enough warmth to keep their bodies above the threshold of collapse. To us it may seem ironic that the creatures who would one day spread across continents relied on forgettability to survive their most dangerous moment. But the soil layers from those years suggest exactly that. Mammal remains are rare but steady. Not abundant, not flourishing, but present. In paleontology, presence in the aftermath of catastrophe is often the first sign of future possibility. Yet even here, one has to be cautious. These mammals were not aware of any future. They did not endure with intention. They simply continued because continuation was what their physiology allowed. Their survival offers a perspective on resilience that does not rely on strength or victory. It reminds us that life can shrink into the narrowest cracks and still persist, that being overlooked can sometimes be an advantage, and that in the long story of this planet, the line between disappearance and endurance is often measured not by dominance, but by modesty. Everything we know about these early mammals comes from the fragments they left behind. Burrow traces hardened into stone, tiny bones fossilized in ancient riverbeds, teeth worn by diets assembled from whatever the broken world still offered. As a humble student of this history, I can only interpret these traces with care and admit what remains unknown. But what seems clear is that when the Earth paused, when ecosystems fractured, when light itself faltered, the ones who had lived in the margins continued. They did not conquer, they endured, and endurance in that silent epoch was enough. Imagine this. After years of dimness, after skies that held dust thicker than any cloud, after forests burned into skeletal silhouettes, a single morning arrives when the light is no longer grey. Not warm, not bright, not yet the sun as the world once knew it, but a faint shift in colour, a suggestion of pale gold returning to a world that had forgotten it. In the decades following the impact, healing did not come suddenly. It came the way moss grows on stone, quietly, invisibly at first, and then all at once when enough time has passed. When the dust finally began to settle from the upper atmosphere, the first change was not the return of heat, but the softening of shadows. For years, sunlight had been strangled by layers of pulverized rock, soot, and sulfate aerosols. Photosynthesis, the great silent engine behind all food webs, had nearly stopped. But dust does not stay aloft forever. Gravity, wind patterns, and precipitation pulled it slowly downward. In sediment cores taken from around the world, there is a measurable turning point where the darkest layers, rich in soot and shocked minerals, begin to thin. Above them lies a lighter band. Geologists sometimes describe it as a transition from despair to possibility. The first organisms to respond were those that ask least of the world. Mosses do not need deep soil. Fungi do not need sunlight. Spores can wait dormant for decades, carried in microscopic abundance across continents. And so the earlier signs of recovery are found in paleontological records. Sudden spikes in fungal spores immediately after the boundary layer. For years after the impact, fungi thrived on the carbon-rich remains of a dead biosphere. They digested fallen logs, burned vegetation, even the animals that had succumbed to cold or hunger. In a sense, they cleared the stage for everything that came after. Then, as sunlight filtered more reliably through the thinning haze, another shift appears in the pollen record. Ferns. This phenomenon is now known as the fern spike, an overwhelming dominance of fern spores found in boundary sediments worldwide. Ferns are pioneers. Their spores travel easily, germinate rapidly, and colonize bare soil without hesitation. They do not demand stable climate or rich nutrients. All they need is moisture and the faintest hint of light. In the years following the impact, ferns coated scarred hillsides, riverbanks clogged with ash, and floodplains stripped of trees. They were the first green the world had seen in a long time. Imagine a landscape once darkened by firestorms beginning to show patches of delicate fronds, each leaf unrolling toward a sun it had never known. The air was still cold, the seasons still unpredictable. But the presence of ferns signalled that the planet had turned a corner. The crisis had shifted from destruction to fragile renewal. In regions where the climate allowed, mosses and liverworts formed damp carpets on fallen logs and exposed rock. Their arrival changed the soil itself. They trapped moisture, slowed erosion, and began the slow process of creating organic matter where none remained. Small patches of green absorbed the returning light, filtered the rain, and stabilized ground that had been stripped to mineral dust. Even in places where ice lingered, trapped by atmospheric instability, mosses crept up to the edges of meltwater pools, turning barren ground into something that could support roots. The return of sunlight also triggered the reappearance of freshwater algae. In lakes and rivers choked with sediment, conditions had been hostile. But clear water is persistent. Particles settle, currents cleanse. When enough sunlight reached the surface, algal blooms re-established photosynthesis in aquatic ecosystems. In cores taken from ancient lake beds, there is a distinct re-emergence of chlorophyll derivatives, marking the revival of the first photosynthetic communities after the darkness. With these early returns came insects, those that had survived underground in wood or in sheltered microhabitats. Their populations did not explode immediately. They expanded the way everything did in those decades. Cautiously, beetles feeding on fungi, small scavengers walking among dead vegetation, flies drawn to moisture-rich pockets. These insects pollinated nothing yet, for flowering plants were still scarce, but their presence accelerated decomposition and soil formation. The earth, wounded, began to recycle its own remains. Eventually, as soils thickened and temperatures rose incrementally with a clearing atmosphere, more complex plants returned. Not forests, those would take centuries. Instead, pioneers such as horsetails, club mosses and early shrubs began to take hold. Their root systems stabilized riverbanks. Their leaves captured light more efficiently than ferns. Their presence shifted the microclimate of the recovering world, altering humidity and shading the ground. In palynology labs, the increasing diversity of pollen types from these early decades forms one of the best indicators that terrestrial ecosystems were awakening. One can imagine a valley that, only years earlier, had been choked with ash and fallen trunks. Now scattered patches of green spread across it, ferns in the lowlands, shrubs on the slopes, moss glistening along the edges of streams running clearer with each season. It would not resemble the lush Cretaceous forests that once dominated the land, but it would be alive in a new way, tentative, youthful, rebuilding. The earliest forest to return may have been composed of hardy conifers, though at lower density and smaller size than before. Their seeds, carried by wind, found purchase in fresh soil. They grew slowly, adapting to colder years and remaining vulnerable to late frosts. But grow they did. Part of this recovery was driven not by plants, but by climate. As dust continued to fall out of the stratosphere, sunlight increased. Each year brought slightly warmer summers. The coldest winters became marginally less severe. Climate models suggest that the impact winter likely lasted several years, perhaps a decade or more in some regions, but it did not last forever. When global temperatures began to rise again, biochemical cycles that had been nearly frozen restarted. Carbon dioxide, once trapped in the upper atmosphere, dispersed or dissolved into oceans. Weathering resumed. Rain patterns normalized. None of this happened rapidly, but slowly, steadily. The sky regained its transparency. With clearer skies came shifts in colour. The world that had lived under a grey-brown haze saw the return of more vivid hues. The blue of shallow lakes, the green of new leaves, the faint gold of sunrise. Early human ancestors would not appear for tens of millions of years, but if anyone had stood on a hillside then and looked out across a recovering plain, they would have witnessed a kind of rebirth that exists only on planetary scales. The sediments recording these decades tell their own quiet story. Layers that once held soot and iridium transition into layers rich with pollen. In each band, the fragments of spores and grains reveal which plants were present, in what quantity, and how quickly they expanded. Ferns dominate first, then shrubs, then trees. It is a succession pattern familiar to any ecological disturbance, but amplified here to continental proportions. What is striking is not the speed of recovery, but its inevitability. Life did not hesitate. It advanced into every clearing, every patch of soil, every inch of ground freed from ice. After an extinction that reshaped the world, the first steps back toward complexity arrived not with grandeur, but with organisms so small and humble they can be held between fingertips. This is perhaps one of the most comforting truths in all of Earth's history. The smallest things are often the first to return. As a student of this deep past, I can only interpret these fragments with humility. Much remains unknown. The timing of recovery varied by region. Some places stayed cold longer, others saw faster regrowth. But the broad outline is clear. After the dust winter, the world began to heal from the bottom up. Fungi, mosses, ferns, shrubs, trees. Light returned, soil renewed, rivers cleared. The planet breathed again. And somewhere in that gradual brightening, the first true colour a wounded world saw was green. As the world continued to brighten, another quiet transformation unfolded in places few eyes would ever see. The soil. Beneath the emerging fern canopies, microbial communities began to reorganize themselves. The impact had sterilized vast regions, but pockets of surviving bacteria and archaea spread outward with each thaw. These microscopic pioneers broke down mineral-rich ash, releasing nutrients locked within it. In doing so, they rewrote the chemistry of the recovering ground. Nitrogen-fixing organisms, for example, began restoring the element that green plants depend on, slowly reintroducing it into the soil after years of atmospheric stagnation. The first plant roots interacted with these microbes, forming tiny symbiotic networks that would eventually become the foundation of entire ecosystems. With sunlight returning and temperatures creeping upward, the hydrology of the land shifted as well. Melting permafrost patches produced seasonal floods that carved new channels across the landscape. These waters carried silt and nutrients into low-lying areas, creating temporary wetlands. In these quiet basins, algal mats formed the earliest stable photosynthetic communities since the impact. Their presence changed the colour of the water from ash-grey to faint green, an early sign that carbon cycling was beginning to revive. As these mats expanded, they produced oxygen locally, microclimates of breathable air under a sky that still carried the memory of darkness. The air itself evolved in subtle ways. Particles continued to settle, leaving behind clearer horizons and gentler gradients of colour. The haze thinned enough for clouds to reform in more predictable patterns. After years of chaotic weather, the atmosphere began to follow cycles again. Rain, once acidic and irregular, became softer and more frequent. These early rains washed salts from the soil, reducing the harshness left by the impact's chemical shock. They also carried spores, seeds, and fine sediments across great distances, scattering the components of renewal from valley to valley. In some regions, particularly those closer to the equator, regrowth moved more quickly. Warmth arrived there first. Moisture pooled in the shadows of still blackened ridges, forming pockets of life where moss thickened the surface and ferns grew tall enough to sway in the wind. These swaying fronds cast the first true moving shadows on the ground in decades, not the sharp silhouettes of conifers or the vast canopies of the ancient Cretaceous forests, but thin, trembling shapes that signalled the return of motion to a world that had been still for far too long. Animal traces also reappear in these early soils, not large creatures, and not in abundance, but small footprints pressed into soft mud near water's edge. Tiny impressions suggesting cautious movement, perhaps insects, perhaps amphibians, perhaps mammals leaving their burrows to forage as warmth and plant cover increased. Their presence did not reshape the land, but it hinted that the foundations of food webs were reassembling. Lakes too recovered at their own pace. As clearer skies warmed the surfaces, stratification patterns returned, allowing deeper waters to mix slowly with the upper layers. This brought nutrients back up from the depths, feeding the modest algae that had reappeared. In some lakes, these algae produced soft oily sheens on the surface, not pollution, but the sign of an ecosystem beginning to breathe again. The world was still fragile. Recovery was uneven. Centuries would pass before forests returned in full. But in the gentle spread of green, the slow cleansing of rivers, the quiet softening of the light, and the reawakened chemistry of soil and water, the planet revealed a truth older than extinction itself. Life does not rebuild from strength. It rebuilds from persistence. What if I told you that sometimes the world moves forward not by building on what survived, but by letting go of what can never return? After the dust settled, after the ferns spread and the soils breathed again, the Earth entered a period unlike any it had known before. The last dinosaurs had vanished, the great marine reptiles were gone, and the skies no longer carried the silhouettes of pterosaurs. For the first time in more than 150 million years, the planet was quiet enough for smaller voices to be heard. It was a silence measured not in hours or days, but in millions of years of opportunity. In the decades after the impact, the world was still raw, scarred by ash and stripped of the ancient forests that had defined the late Cretaceous. But as centuries passed, a slow stabilizing began. Temperatures rose as sunlight returned. Rainfall patterns settled into predictable rhythms. Rivers carved new courses through loose sediment. Where old landscapes had been erased, new ones emerged, shaped by erosion, ice, wind, and the simple force of gravity. The continents themselves were still drifting, moving in slow patterns that would define the Paleogene. In this rearranging world, niches opened like unclaimed rooms in a vast, newly built house. The creatures that stepped into these rooms were not grand or imposing. They were the descendants of the small mammals that had hidden in burrows during the worst of the darkness. Over thousands of generations, as food webs reassembled and plant diversity increased, these survivors expanded into shapes and lifestyles almost unimaginable when they were still scurrying beneath the feet of giants. Some grew larger, testing bodies built for browsing rather than hiding. Others took to climbing, living in the branches of trees that had only recently reclaimed the sky. Some became swift runners across open plains. Others adapted to rivers and lakes still reshaping themselves after the tsunamis. This radiation was not explosive in the sense of a sudden burst. It was gradual and unfolding. Evolution does not rush. It tests possibilities, repeats patterns, and allows chance to sculpt form. What made the early Cenozoic unique was not speed, but space, the ecological space left behind when an entire dynasty vanished. Without massive herbivores consuming vegetation, plants grew thicker and spread faster. Without enormous predators dominating the night, smaller hunters could test new strategies. This openness gave rise to ecosystems that no longer resembled the Cretaceous. Instead of coniferous giants and towering cycads, broad-leafed plants expanded. Early flowering species diversified. Forests took on shapes, colours and scents that had never existed before. Climate oscillated across these early millions of years, but in ways that nurtured diversity rather than restricting it. There were warm periods when tropical forests stretched far into higher latitudes, and cooler intervals that reshaped grasslands and wetlands. In each cycle, mammal lineages adapted. Bones from this time show an extraordinary variety. Long limbs, powerful jaws, delicate fingers, complex teeth capable of handling new diets. Some lineages experimented with gliding membranes. Others enlarged their senses of smell and hearing. Life moved into the air, the water, the canopy, and the open ground. If one could walk through these landscapes, perhaps 1 million years after the impact, one would see a world that felt young. Not in the sense of immaturity, but in the sense of newness. Ecosystems still untested, species still discovering their limits. Many of the creatures would seem familiar in outline, yet alien in detail. Paleogene mammals often blended ancient features with emerging ones, a reminder that evolution works not with a plan, but with whatever raw material is available. In this era, birds also diversified, filling aerial roles once held by pterosaurs. Insects expanded into the fresh bloom of flowering plants. Reptiles persisted, but with diminished dominance. Amphibians reoccupied wetlands restored by rainfall and sediment flow. Everything was in motion, not in haste, but in a steady reshaping guided by climate, vegetation, and the simple principle that empty ecological space does not remain empty for long. The landscapes themselves transformed, volcanic fields cooled, floodplains stabilized, new mountain ranges uplifted in slow increments, altering rainfall patterns and carving rain shadows across continents. With each change came new habitats, arid basins, lush valleys, sprawling forests, and vast inland seas. These environments acted like laboratories, isolating populations and allowing them to diverge in form and behaviour. Over millions of years, this branching produced the early outlines of the modern world. In the sediments recording these ages, paleontologists find a gradual return of biodiversity, not the same as before, but comparable in richness. Ferns gave way to forests, shorelines filled with new mollusks. Rivers supported fresh assemblages of fish and amphibians. Even the deep oceans, which had suffered the longest, eventually regained complexity as plankton communities evolved into new shapes. Every recovery, whether on land or in water, followed the rhythm of ecological succession, from simplicity to complexity, from scarcity to abundance. What makes this period especially profound is that it marks not only the recovery of life, but the resetting of the planet's evolutionary direction. Extinctions do not merely remove species, they remove competition, constraints, and histories. The disappearance of the dinosaurs did not guarantee success for mammals or any other group. It simply allowed new stories to be written. Some of these stories endured, many did not. But they were all born from the same moment of planetary disruption. As centuries grew into millennia, and millennia into millions of years, the Earth carried the memory of the impact not in scars alone, but in the structures of its ecosystems, the shapes of forests, the presence of certain predators, the routes taken by rivers, the very distribution of continents. All were influenced indirectly by the shifts that began when the asteroid struck. Even today, iridium layers buried beneath our feet mark that turning point. Every cliff exposing the boundary tells the same quiet truth. The world that came after was fundamentally different from the one before. The final lesson of this extinction is not one of destruction, but of transformation. The end of the dinosaurs cleared space for lineages that had lived in shadow. The reshaping of climate created opportunities for new forms. The slow healing of ecosystems allowed diversity to expand in directions impossible under the weight of the old order. None of this was destined. None of it was guaranteed. It was simply the result of life's persistent tendency to fill every available niche, to adapt, to explore, to continue. And in the quiet that followed the fire, the world did not end. It simply changed direction, carrying the faint memory of that day all the way to us. As the early Cenozoic unfolded, something even more subtle began shaping the path of life, the return of rhythm. For years after the impact, the planet's seasons had been erratic, its skies unpredictable, its temperatures swinging in ways that offered little continuity. But as atmospheric clarity improved and ocean circulation regained its momentum, the world settled into cycles again. Winters grew distinct from summers. Rainfall followed patterns that plants could anticipate. Light lengthened and shortened with reliable grace. This consistency, more than warmth alone, allowed ecosystems to coordinate themselves, weaving new relationships across landscapes that had once been stripped to their foundations. Trees were among the first to respond to the return of these rhythms. Their growth rings, visible in fossilized trunks from the early Paleogene, show the re-emergence of seasonal pulses. A wide band for the generous months, a narrow band for the lean ones. These rings become a record not of destruction, but of renewal. They speak of a world learning how to breathe in long, steady intervals after a period of broken breaths. Broad-leafed species spread across floodplains. Early hardwoods emerged in patches, and conifers returned to higher elevations where the cool air still lingered. With this arboreal resurgence came something the world had not heard in a very long time, the rustle of wind through leaves. Rivers changed as well. Without massive dinosaurs stirring sediment across riverbanks, the waterways defined their own courses, unrestricted by the great herds that once drank from them. New meanders formed, wetlands expanded. In these restructured hydrological systems, amphibians found niches, insects diversified, and fish adapted to altered nutrient flows. Each organism that settled into these new habitats became a thread in a tapestry being rewoven by time itself. Even the air began to sound different. Insects, which had survived the impact tucked inside wood, soil, or water, gradually reclaimed the soundscape. Their buzzing, once overshadowed by the calls of gigantic reptiles, became one of the dominant voices of the early Paleogene. The acoustic world changed from thunderous footsteps and resonant bellows to the delicate drone of wings and the soft scurry of mammals in underbrush. In many places, this gentler soundscape persisted for millions of years. Geology played its part, sculpting opportunities from stone. Mountain-building processes slowly lifted new ranges. Ancient volcanic fields eroded into fertile basins. Sea levels shifted, opening land bridges and isolating islands. Each geological change acted as an evolutionary invitation. Populations became separated, diverging in form and behaviour as environments altered around them. Some lineages adapted to life on open plains, others climbed into forest canopies, some returned to the water, some remained small and nocturnal as their ancestors had been during the dark years. What is remarkable about this time is not the speed at which life diversified, but the way it layered complexity upon a planet that had recently been reduced to its simplest state. Every new branch of the evolutionary tree sprang from ancestors that had survived by the narrowest margin. Every expanding species carried within it the genetic memory of scarcity, yet now existed in a world of opportunity. The Earth of these millions of years after the impact was not simply a healed world, it was a reinvented one, and though none of its inhabitants could know it, the direction taken during this quiet reconstruction would echo far beyond their lifetimes. The forms tested here, the landscapes reshaped, the rhythms restored, all of them set the course for the ages that followed, guided not by catastrophe, but by the resilient patience of life continuing to unfold.